Good morning, welcome to new lecture. Today I will talk about stress transformations using Mohr circle. So today's topic is stress transformations using Mohr circle. First point we should pay attention, it is this point, stress and strain. They are directional. Once we are talking about stress or strain, we should talk about the direction too. In which direction we can have that stress or strain. So stress and strain, both they are directional. And maybe we have stress and strain in one orientation, in one direction. So we know stress in one direction, we know strain in one direction. In order to find stress in another direction, we should be able to transform stress from one direction to another direction. Whenever we want to design any structural member, any member we want to design, we should design to the maximum stress. We should find maximum stress and compare that maximum stress in that member with the allowable stress. So we should be able to find stress in any direction or any orientation. So maybe we know the stress in one direction, and that stress in one direction, it is less than allowable stress, but that stress can create another stress in another direction. It is bigger than allowable stress, and we will have failure in that direction. So we should be able to find the maximum and minimum stress direction and orientation. In order to find that, in previous session we came up with formula. There is another graphical way first developed by Otto Mohr. Otto Mohr was German civil engineer. He developed this method, graphical representation of the stress transformations. Let's see how we will find stress in another direction using this method. This is graphical method. It is easy to understand. In order to find that, Otto Mohr invented that around 1880s. He developed around this date. He was German civil engineer, and he came up with two-dimension graphical representation of stress transformation. If we have one stress element, assume we have this stress element, and this is x direction, this is y direction. We have, once we have a stress element, this plane is perpendicular to the x direction. We call it x face of the element. In the x face of the element, normal stress we will represent with sigma x. And in order to have this element in equilibrium, we should have sigma x in other face in inverse direction. This face, it is y face of element because it is perpendicular to the y direction. So this normal stress we will show with sigma y. Normal force means sigma, because it is in y face of element, we will call it sigma y. It is in x face of element, we will call it sigma x. And you know normal force, it is perpendicular to the face. Shear stress, it is tangent to the face. This is x face of element, so shear stress here will be tau, because it is in the x face of the element, we will show with tau x, and because it is in y direction, tau x y. So we will have this shear stress will produce another shear stress in the perpendicular direction. Again, this is tau here because this is shear stress tangent to the surface and it is in the y face of the element, so tau y, and it is in the x direction, tau yx. And we will name other stress in similar way, so this will be tau x, tau yx. Tau yx, and this will be again tau xy. Here, this is x face of the element, and it is positive x face because normal to this plane, it is in the positive x direction. And tau xy, because in positive direction of the y, we will call it positive shear stress, or that shear stress rotate this element counterclockwise, we will call it positive shear stress. In some textbook, maybe you will see inverse direction positive, no problem, you should be consistent. As long as you are consistent, it will not create any problem. I call this shear stress is positive, it wants to rotate this element counterclockwise. So this one rotates clockwise, it will be negative, and this will be again negative, this will be positive. Anyway, then we will have Cartesian coordinate. Horizontal axis, we will call it sigma, normal stress. Vertical axis, positive, I show downward, and I will call it tau, shear stress. In some textbook, again, you will see tau upward is positive, no problem. Here, because I assume counterclockwise rotation positive, tau downward positive, it is good, because in that case, rotation on the coordinate will be exactly the same direction as a rotation on the element. Later on, you will see why. So this is positive, this is positive. First step, we should find the average normal stress. Average normal stress or mean stress, it will be equal to sigma x plus sigma y divided by 2. So, average sigma normal stress or sigma mean and 0 will be first point on this coordinate. It will represent the center of one circle. So assume it is here. This is sigma m, average normal stress. It means sigma x plus sigma y over 2, or mean stress, and 0. So always center of the Mohr circle will lies on the sigma axis. Then we will look at to the x face of the element. X face of element, here I have sigma x and tau x, y. If I have number, it will represent one point in this coordinate. So it will be something like this. Here it is sigma x and tau x, y. This is point B, this is point A, for example. Then we will look at to, this is center point. This is x face. In the y face, we will have another point, point C, for example. We will have sigma y and tau yx. Here tau yx direction is negative minus tau yx. If I show that point in this coordinate again, it will be, because this is negative direction, this is positive direction, and this will be, for example, this point, it is point C. Something like this, point C. Then if we will attach these points together, it will represent the diameter of this circle, point A, point B, point C. The radius, it is AB. Pay attention, normal stress, we will call it positive. If it creates tension inside of the element, or it is tensile stress, you see, this direction will create tension inside of the element, so sigma x positive. Here sigma y is create tension as well, so it is positive. If it is tensile stress, it is positive. If it is compressive stress, it is negative, or if it creates compression inside of the element, it is negative. Here we want to find the radius, because if we rotate radius respect to point A center, we can draw one circle. In order to find radius length, it is A, B length, it is R. It is easy to find R. Why? Because if you pay attention here, this is right angle triangle. So this height, it is tau xy. And from point A to point B prime, so BB prime is equal to tau xy. AB prime is equal to here, is equal to AB prime. Look at here. What is this? This is center point sigma m, or mean stress. What is this point? It is sigma x. So from here to here it is sigma x. AB prime will be sigma x minus sigma m. So in right triangle, we have both legs. We have AB prime, we have B prime B. So AB will be equal to square root of BB prime plus AB prime squared. So AB in this right angle triangle will be square root of BB prime squared, BB prime squared plus AB prime squared. That will be equal to, if I plug these values, it will be tau xy squared plus sigma x minus sigma m squared. So square root of tau xy squared plus sigma x minus sigma m squared will be equal to AB, that is equal to radius for Mohr circle. If we rotate this R respect to point A center point, we will draw one circle. I show this circle with dashed line. Intersection of this circle with sigma axis, this and this point, the maximum point we will show with sigma 1, the minimum point we will show with sigma 2. This is maximum normal stress, and you see, because it is on the sigma axis, the shear stress is 0. It says minimum normal stress again because that point it is on the sigma axis. Again, shear stress tau is equal to 0. So sigma 1 and sigma 2, both they will represent principal stresses. And if we look at this maximum shear tau max will be equal to radius of this circle. So the maximum of shear stress will be equal to radius of this circle. I draw this picture one more time with key points and explain one more time, then we will solve one example. So what we had here x-axis we call it normal stress, y-axis we call it tau, downward I assume it is positive. Here it was center point, point A coordinate was mean stress and 0. Then we had point B was stress on the x face of the element. Stress on x face of element, it means this face perpendicular to the x direction, it is sigma x and tau xy. Point C was stress in the y face of the element. So sigma y and negative tau yx. If we show this point, this will be point C, sigma x, tau xy, sigma y, negative tau yx, and R radius. How we will find R? In order to find R, we should find in this right angle triangle this leg length. This leg length, if I write it A, B, B prime, AB prime is equal to sigma x minus sigma m, and BB prime was equal to tau x y. So from here, the radius will be equal to square root of tau xy squared plus sigma x minus sigma m squared. If we rotate this radius respect to point A, we will create one circle. The intersection of this circle with horizontal axis, we will call it sigma 1 and sigma 2. It is easy to understand. Sigma 1 is maximum stress, normal stress, and in this point shear stress is 0, because in this point the coordinate for shear stress is 0, and sigma 2 is minimum normal stress because the value is minimum, and here again shear stress is 0. And tau max, it is this height, because this shape is circle, so if we rotate radius, this will be equal to R. So tau max will be equal to radius of Mohr circle, which is equal to tau xy square root of tau xy squared plus sigma x minus sigma m squared. Mean stress or average stress, average normal stress, it was sigma x plus sigma y over 2. From here, principal stress, maximum normal stress, sigma 1, will be mean stress plus radius. Sigma 2, minimum normal stress, will be again sigma m minus radius. So if I call this angle alpha, look at here, from B, if we wanna reach to the C, it is a straight line. So entire angle we should rotate from B to C, it is 180 degrees. So straight line angle, it is 180 degrees. So this angle, it is 180 degrees. If we rotate from point B counterclockwise 180 degrees, we will reach to point C. Point B belongs to the stress on the x phase. Point C belongs to the stress on the y phase. So if we rotate on Mohr circle 180 degree, we will convert x phase to the y phase. But on the element, the angle from x to y, it is 90 degree. So rotation on Mohr circle is always 2 times of real element rotation. So if I rotate this radius alpha, I will reach to the sigma 1. So I can find alpha is inverse tangent of, in that triangle, alpha is equal to inverse tangent of BB prime divided by AB prime. That is equal to tau xy divided by sigma x minus sigma mi. Why? Because this is right angle triangle. Alpha, tangent alpha is equal to BB prime divided by AB prime. That is equal to, so if I want to find angle alpha, it will be inverse tangent of tau xy, because this height is tau xy, divided by this length, which is sigma x minus sigma mean or average. After I find alpha, theta p1, it means the angle we will rotate the element and face of elements will be towards to the principal stress, sigma 1 and sigma 2. It will be alpha over 2 counterclockwise. You see here, if we rotate this radius respect to the center, alpha counterclockwise, we will reach to the sigma 1. So if we rotate element, half of that, alpha over 2, this face will be towards to the sigma 1. I can define another angle. I can define, for example, let's see, if I define that alpha, I can define this angle beta, and you see beta is equal to 180 degree minus alpha. This angle is beta. It is entire angle 180 degree minus alpha. So theta P2 will be half of that, beta over 2 clockwise. If we rotate this radius, beta angle will reach sigma 2. So if we rotate this face as much as beta over 2 clockwise, this time rotation is clockwise. You see, we should rotate clockwise to reach the sigma 2. That face will be towards to the minimum stress. So if I want to draw the element, I should draw like this here. This is initially our element. We should rotate that counterclockwise, alpha over 2 or theta p over, or theta p1 is equal alpha over 2 or theta p1. In that case, if I show with another color, element will rotate like this. Again, the same square stress element, we should rotate theta P1 counterclockwise. If we rotate like this, in the X phase, we will have maximum stress, sigma 1 and sigma 1. In the Y phase, we will have minimum stress, sigma 2 and sigma 2. And because this is corresponding the principal stress shear. Stresses on these sides all are 0, so we don't have shear stress in this direction. If we want to reach to the maximum shear stress, we should rotate this as much as phi, this angle, as much as phi, and we should rotate clockwise. So I can write phi is equal to 90 minus alpha, because entire this angle is 90 degree. 90 minus alpha will be phi, and maximum shear stress direction theta and this S will be phi over 2, half of that. So if I have again element like this, I should rotate that element clockwise, theta S. In that case, this will be new position of the element. Here on faces, we will have maximum shear stress, and we will have average normal stress or mean stress. Because in this position, shear stress is maximum for this point. If I put this point name, for example, D, shear stress magnitude is maximum, and normal stress is from here to here, it is equal to average or mean stress. So if we rotate this radius, phi on Mohr circle, in real element we should move half of that, so phi over 2. The x phase will be towards to the maximum shear stress, and the normal stress on faces, on all faces, will be equal, and that is equal to mean stress. This is the way we will draw Mohr circle. Let's look at one numerical example. If I have one stress element, and the state of stress on each face is given, this is 5 KSI, 12 KSI, 8 KSI, 5 KSI, again 12 KSI, 5 KSI, 8 KSI, and 5 KSI. We have a stress element, and we know stress on each side, each face. This stress can create maximum stress in another direction, maximum normal stress, and it can create maximum shear stress in another direction. What is the magnitude of that maximum normal stress? We don't know. What is the orientation or direction we will have that maximum normal stress? We don't know. What is the magnitude of maximum shear stress? We don't know. In which direction we will have that maximum shear stress? We don't know. In order to answer all these questions, we need to draw Mohr circle. We need to do stress transformations. We can use the formula I found last session, or we can draw Mohr circle. Let's look at the Mohr circle. So, we should find the point A. Point A, it is center point for circle. It is average normal stress. So sigma x plus sigma y divided by 2. Pay attention here. Sigma x here, it is negative 12 KSI because it is compressive stress. Sigma y, it is positive 8 KSI. So the average value, point A coordinate, will be negative 2 and 0. Point B will be stress on the x phase of the element. On the x phase of the element, the normal stress, it is negative 12. Shear stress, it is negative because it rotates element clockwise, it is negative 5. Stress on y phase of element. In y phase of element, normal stress, it is tensile stress, so it is positive 8. And shear stress, because it rotates element respect to the center point counterclockwise, it is positive 5. So we have the center point coordinate, we have two other point coordinates we can attach together. It will be diameter of the circle. We can rotate respect to the center, and we will draw that Mohr circle. So first step, we should show two axes. The horizontal axis, we call it sigma, the vertical one, tau, positive vertical downward. Here, the average normal stress, it is negative 2. For example, here, point A, negative 2, because it is in negative side of sigma. The x phase, it is negative 12, negative 5, for example, something like this. We call it point B, point A coordinate, it is negative 2 and 0. Point B coordinate, it is negative 12, negative 5. And we have point C coordinate, it is positive. For example, point C coordinate, it is positive 8, positive 5. So we should now show our circle. It will be something like this. I think I should use another black. Okay, this is circle. Now, let's find the maximum and minimum stress. So we should find sigma 1, sigma 2, and tau max. This is maximum normal stress, sigma 1. This is minimum normal stress, sigma 2. And we will have maximum shear stress here. So this is coordinate for here. It is tau max. Coordinate for here. It is sigma m and tau max. And you know tau max is equal to radius for this circle. So now, if I rotate this radius, alpha, I will transform point B to the sigma 2. So if I call alpha to theta P, it will be equal to inverse tangent of tau xy for that point, it is 5 divided by, in this triangle, this height, it is 5, by this leg length, it is 12 minus 2. So here it is negative 12, here is negative 2. So this length it will be 12 minus 2. From here, alpha will be equal to theta P. That will be equal to 26.57 degree. And from there, theta P will be equal to 13.28 degree. That is the direction we should rotate point B reach to the sigma 2. We find that direction. And we should do this rotation. You see, we should rotate counterclockwise, so counterclockwise. On the other hand, we can find sigma mean or sigma 2. Sigma 2 will be equal to the center point coordinate, or sigma m minus 2, minus radius. The radius, if we find the radius for this, radius is equal to tau max, that is equal to tau xy squared, which is 5 squared, plus 12 minus 2 squared. So r will be equal to square root of 5 squared plus 12 minus 2 squared. That will be equal to 11.18 KSI. So sigma 2 will be equal to sigma m minus r. That is 11.18 that will be equal to minus 13.80 KSI. Sigma 1 will be equal to sigma mean plus the radius, so minus 2 plus 11.18, it will be equal to 9.18 KSI. So this is 9.18 zero coordinate, and this point it is minus 13.18 0. Now let's look at to the element. If we have this element, initial position, we have that element, and this is x direction. If we rotate as much as theta p is equal to 13.28. 13.28, we show element like this. This will be the direction of the principal stress. It means in this direction, and because let's see, we will have the principal direction. If we rotate B, theta P counterclockwise, we will reach to point B. So in this phase we will have sigma 2. Sigma 2 is negative 13.80, so we should show compressive stress. It will be 13.18. Other side again, it will be 13.18 KSI. So here in this phase we will have tensile stress. We will have 9.18 KSI and 19.18 KSI. So principal norm stress, it means maximum and minimum normal stress, will be positive tensile 9.18 KSI and negative compressive 13.18 KSI. In which direction we have? If we rotate 13.28, in that case this phase will be towards to the minimum stress. We are rotating on the Mohr circle alpha, half of that we should rotate element, and this phase will be towards to the maximum tensile stress, and so we should rotate element 13.28 counterclockwise. This is about normal stress. Let's look at today shear stress. Shear stress we should find phi angle. Phi angle will be equal to phi angle will be this angle phi here. Phi will be equal 90 minus alpha. That will be 90 minus 26.56 is equal to 63.44 degree. And as I mentioned, the maximum shear stress direction theta s is equal to phi over 2. That will be equal to 63.44 divided by 2, that is equal to 31.72 degree. And we should rotate here. If we wanna reach from point B to here, we should rotate clockwise. So if this is initial element, this is x direction, we should rotate theta s is equal 31.72. Element will be like this. In that case, in the face of this element, we will have maximum shear stress, and it is negative, So it will be in this direction, negative 11.18, because maximum shear stress is equal to radius, and because it is in this side, this side is positive, this side is negative.